Hey, it's Sukrit from Stamcoder, and today we're going to look at continuity and differentiability. Let's look at the definition of those two words. A function is differentiable at a point if its derivative exists at that point. A function is continuous at a point if there are no abrupt changes in the value of the function at that point. So what exactly do we mean by no abrupt changes? Well, let's look at some examples. Over here I have three functions. In the first one over here, at this point, the entire function is a parabola, but at this point, we can see that the value of the function is actually this floating point all the way up here. It doesn't just follow the standard parabola line. There is a hole in the function. We can see that this function is disjointed. It has an abrupt change, and so the function is not continuous at this point. Let's look at this function over here. We have an asymptote going down the middle over here. So the function is clearly not continuous over here. Why is that? Because the function doesn't even exist at that where this asymptote is. And anyways, on this side of the asymptote, the value of the function is positive infinity. On this side is negative infinity. It doesn't even exist where the asymptote is. So clearly it's not continuous over there. Now let's look at this function over here. The function, it does exist over here at this point. However, the function is disjointed. There is an abrupt change in the function. You can see it goes from down here all the way to up here. It's like a step up, and so it is not continuous. There is an abrupt change at this point over here, an abrupt change. Now, we say that an entire function is continuous if it is continuous at every single point. So the entire function cannot contain any abrupt changes. If it even contains one abrupt change like this, it is not a continuous function. So basically the function must exist for the entire domain. Now, what is the relationship between continuity and differentiability? Well, here it is. If a function is differentiable at a point, then it has to be continuous at that point. And this kind of makes sense. If a function has an abrupt change or it does not exist at a point, well, how can we even take its derivative? Then it basically implies that if a function is not continuous at a point, we cannot take its derivative at that point. Consequently, if a function is differentiable at a point, then it has to be continuous at that point. Now, something's interesting to see. Let's look at these two functions over here. Do you think these two functions are continuous or not at these points? Well, they are continuous. There is not exactly an abrupt change. These two functions are indeed continuous at these 2 points. However, are they differentiable? They are not differentiable at these points. Let's just look at the derivative of this function as an example. I'm just going to roughly draw the derivative, and this actually looks something like this. And there is an asymptote. So over here you got an asymptote. Obviously, where there's an asymptote, the function doesn't even exist there. And remember, this is the derivative of this. So at this point over here, the derivative of this function, there's actually an asymptote. So that means that the derivative of this function does not exist at this point. The function is continuous at that point, but its derivative does not exist. There's an asymptote there instead. That shows that this implication does not work the other way around. So continuity does not imply differentiability. Differentiability does imply continuity, but you cannot switch that statement around. Now let's look at a more formal definition of what it means for a function to be continuous. When I say there should be no abrupt change, it's got to satisfy these three conditions. And when I say a function to be continuous, I actually mean to be continuous at a point. First, the function must exist at that point. So clearly, if there's an asymptote, that function does not exist. It's not continuous at that point. Secondly, the limit of a function must exist at that point. Let's look at this function for an example. The limit coming from this side and the limit coming from this side are actually going to be different, where there's this step over here. And so we can say that the limit of this function does not exist at this point. And so it cannot be continuous at that point. Thirdly, the limit must equal the value of the function at this point. Clearly over here, if we try taking the limit of the function as it approaches this point, we'll actually get the point where this hole is right now, but that's not equal to the value of the function. The value of the function is actually this point up here. So this function over here at this point, it violates this third condition. But if a function satisfies all three of these conditions at a point, then the function is continuous at that point. And if a function is continuous at every single point, then we just say that the function is continuous. So for a function to be continuous, it's got to be continuous at every single point. I hope you found this video helpful, and I look forward to seeing you in future lessons.